Well, good evening, everyone. Thank you for coming out. I'm going to start with an overview on a series of issues around global water resources. I'm going to talk about sort of the state of water where we are, some of the ways we might think about some of the water challenges that face us, and a little bit about some solutions. I'm going to turn it over to Jay after that. Jay's going to talk about his expertise in a wide range of areas, including especially the particular problem of groundwater, which is a piece of this big puzzle, and California drought and some other things as well. And then I think we'll be happy to take questions after that. So I'm going to talk about peak water and the global water challenge and what it looks like. I'm going to talk about water and the issue of climate change. What do we see happening? What can we expect in the coming years? I'm going to talk about water and conflict. That is not the science piece of this, but the connection between water and politics, which is a big part of the water picture worldwide. And then I'm going to talk about some solutions, where we might go in terms of solving the challenges that we're wrestling with around the world and in the United States. Water is connected to everything. It's connected to energy, infrastructure, ecosystems, agriculture, the connection between forestry and public health. There's strong connections between water and energy, water required to produce energy, energy required to produce and deliver our water resources. And it's one of the reasons why I'm so interested in this issue. It's given me an opportunity to dig into a wide range of environmental issues, from the global to the local. I'm going to talk about peak water. A colleague of mine and I wrote a piece on peak water in the Proceedings of the National Academy of Sciences a few years ago, in which we talk about the issue of peak water and what it means, and we define peak water, and I'll talk a little bit about that tonight. And let me start with this curve. This is the exponential growth curve that all of you are familiar with. It's a curve that's behind many of our environmental challenges worldwide. And we see exponential growth curves in all sorts of places, in all sorts of ways. We see it with population. This graph in the upper left is global population from the year 1000 to the year 2000, the last 1,000 years of global population growth, showing an exponential growth in the world's population, and it's 7 billion today, and it's continuing to grow. This curve in the bottom right is global concentration of carbon dioxide in the atmosphere over the last 1,000 years, and it also shows the exponential growth in CO2 concentrations in the atmosphere. This is the Industrial Revolution in many ways, that concentration of CO2, and we see it with other greenhouse gases as well in the atmosphere. And this is the climate problem that faces us. The second curve I'm going to talk about is this one. It's the classic exponential growth followed by a peak, followed by a decline in something. And again, we see this kind of a curve in all sorts of dynamics, all sorts of environmental statistics around the world. We see it in oil production. And in fact, the concept of peak oil has preceded the concept of peak water by many years. And this is a graph that shows peak oil production in the United States from 1900 to the year 2000. And it showed that peak oil in the United States was reached around 1970. And that's when the production of oil in the United States maxed out, and we started to see a decline in oil production in the United States as the cheapest, easiest oil resources were tapped first, and the next resources were harder and harder to get. Oil production has continued to increase in the world as a whole, but increasingly there's a question about when we're going to reach peak oil in the world as a whole and start to see a decline in the production rates of oil. And that's going to be a function of the resource itself. It's going to be a function of technology. It's going to be a function of economics, all sorts of things. But we see this increase, peak, and a decline in all sorts of resource issues around the world. And the one on the bottom right is a capture of Atlantic cod, the fish from the cod fisheries from about 1950 to about 2010, showing an increase in our ability to capture cod in the Atlantic, peaking around 1980, and then a decline in cod production. And cod production has dropped to a tiny fraction of its peak production. as we overfished the cod industry. And as it became more difficult to find cod, as the populations plummeted in the Atlantic, it's another example of a resource depletion curve, if you will. And I'll talk about this curve in the context of water moving forward. And then this is the third curve I want to talk about. And it's exponential growth followed by a decline in the rate of consumption of something, and then a leveling off of extraction or resource use or something. And we see this kind of curve, typically called the logistics curve, in all sorts of statistics and dynamics as well. We see this with technology penetration. This is a curve of market penetration of telephones, landlines, if you will, from 1900 to the year 2000, showing, in a sense, the invention of the telephone. Everybody started to buy a telephone and put a telephone in their homes. And then finally, when everybody had a landline or two, we saw leveling off of the market penetration at basically 100% in the United States. And we see the same kind of curve with all sorts of new technology. We see it with cell phone technology. Cell phones are invented, they start to get cheap, everybody starts to buy one. Once you have one, okay, maybe two, but one, everybody's got one. And you see the classic logistics curve. We see it in other things as well. This is cumulative dam capacity worldwide from about 1850 to the year 2000 that shows 1850, the dam capacity, the storage of water behind dams in the world was very low. The technology for building big dams was developed in the late 1800s, early 1900s, 1920. We started to build big dams on big rivers. We saw an exponential growth in the storage of water behind big dams, and then a leveling off. And we saw leveling off because we built on all the good dam sites and some not so good dam sites. It became more expensive to build big dams. Government subsidies for building big dams, which were very significant in the middle part of the 1900s, started to decrease. Certainly in the United States, we're not subsidizing massive federal interventions in big dam construction anymore. We started to understand the environmental implications of building big dams, and there was growing environmental movement opposing big dam construction, and so the storage capacity started to level off. I think we may see some new dams built in the future, but we're not going to see that exponential growth in the middle part of this curve that we saw as well, and that's the logistics curve for, in this case, storage of water behind big dams. These three curves, the exponential growth at peaking followed by decline, or the exponential growth followed by leveling off, and then a sustained something, are important in a lot of different ways, and they're relevant for this concept of peak water. So I'm going to come back to this question about peak water in a moment, but before I do, water is a renewable resource, mostly. We have renewable and non-renewable resources, and let me define what I mean by that. There are many ways to define non-renewable or renewable, but these are, I think, some of the best ways to think about the issues. Non-renewable resources are stock limited. Renewable resources are flow limited. The amount of a non-renewable resource that you can tap into depends on how much is there. Oil is a classic non-renewable resource. It's created over millennia, millions of years or longer. It's laid down. It's non-renewable on a time scale of interest to humanity. The amount of oil we can get out of the ground is limited by the amount that's there, by the stock. Now, the truth is it's limited by more than that. It's limited by technology, it's limited by economics. We'll never pull out that last barrel of oil. But if you could, you can't have any more. It's limited by the absolute stock that's available to us. Renewable resources are not limited by stock, they're limited by flow. Think of the sun. The sun is a renewable resource, at least on the billions of years that we really care about. It's going to run out eventually, but we aren't going to care. But it is limited. Our ability to tap solar energy is limited by our ability to capture solar energy. The flow that hits the Earth's surface, in theory, we could capture all of that. Not in practice, but in theory. And then once you capture that, you can't have any more. So it's limited by our ability to tap into the flow. And water is the same way. Interestingly, water exhibits characteristics of both renewable and non-renewable resources. Most of our water use is renewable. Think of the hydrologic cycle. Water evaporates, it forms clouds, it condenses, it falls out as rain, it runs off back into the ocean where it evaporates again. That's the hydrologic cycle, and it's renewable. The amount of water in a river this year has no effect on how much water is going to be available next year. Next year, it's a renewable cycle. And our withdrawal of water from a river has no effect on how much water nature is going to deliver to us next year. It's renewable. Interestingly, though, there are some non-renewable stocks of water. And Jay's going to talk a lot about this with groundwater, but there are some groundwater stocks that are sort of like oil. They're non-renewable in the sense that they were laid down over millennia, over thousands or even longer, thousands of years or longer periods of time. And when we pump them out faster than nature recharges them, they're non-renewable, and groundwater levels drop, and we have a problem. And Jay's going to talk about that a lot, I know. But you should understand that water exhibits both renewable and non-renewable characteristics, and that's really important from a water policy perspective and a water management perspective. So, I'm going to define 3 peak water terms using those curves that I was just talking about. So, here's the logistics curve. And the definition of peak renewable water is that there is a limit to how much renewable water we can pull out of a system. And that limit is the total flow of a renewable resource. So think about a river, again, a renewable resource. We start to take water out, our demand increases, we take more and more, and then we get to the maximum. We get to the total renewable flow. And that's all you can have. You can't have any more. Once you take the entire flow of a river, you're at a limit. And increasingly around the world, we're reaching peak renewable limits on our ability to extract water from even a renewable system. And a good example is the Colorado River. Well, all right, before I get to that, it does beg the question, how much should we use? In many rivers around the world, we're taking the entire renewable flow. And it causes ecosystem problems, it causes political problems downstream. So the ability to take the total flow of a river doesn't mean necessarily that that's a good idea. But that's a political question, not a technical question. So here's the flow of the Colorado River, measured at what's called the southern international boundary, the southernmost border where we gauge river flow before it reaches the delta. The delta of the Colorado River is actually in Mexico. The Colorado River is shared by 7 states in the United States and Mexico. And we have allocation agreements among the 7 states. We have an international treaty with Mexico about allocations of flows. But this is the measurement of the flow in Mexico. And you can see a lot of things in this graph. Do we have a laser pointer? Yes. You can see, first of all, ups and downs. So the x-axis is 1905 to 2005. 1905 to 2005, you see lots of ups and downs. The y-axis is the total flow in million cubic meters. So the ups and downs are the natural variability of the river. We have wet years, we have dry years. This is true of any river. In 1905, there were no big dams on the Colorado River, and not that many big cities in the southwestern part of the United States, and not much irrigated agriculture. But over time, we started to take more and more water out of the system, and flow at the southernmost measurement point started to go down. We built big dams, and we built a lot of big dams on the Colorado River to store water, and then we built pipelines and aqueducts to take that water and distribute it to irrigated agriculture and to the big cities. Southern California gets a lot of water from the Colorado River. Phoenix, Tucson, Las Vegas, the big cities are often completely supplied by water from the Colorado. It's the only big river in the southwestern United States. And over time, eventually, we took all of the flow of the Colorado River. We reached peak renewable limits on the Colorado River. Now, Occasionally, in a really, really wet year, if the reservoirs are full, a little bit of flow will reach the Colorado River delta, the mouth of the delta, but not really. We've maxed out on the Colorado River. We can't mostly have any more water on the Colorado River, even if we wanted it. And that's a peak renewable limit. I showed this in a little version. This is global reservoir capacity. We started to build big dams. The y-axis is cumulative reservoir storage capacity in cubic kilometers, the total amount of water stored behind dams. And you can see we store 6,000 or 7,000 cubic kilometers of water behind big dams around the world. So much so that in fact we're altering in a tiny way, the orbital dynamics of the Earth, because we've shifted where water is stored on the planet. That's another story. But we've sort of maxed out. We'll still build a few more dams. There's certainly parts of the world where we need new dams, where there is insufficient storage, where we need it for droughts, we need it for floods. But we're not going to see a repeat of this exponential increase in storage volumes behind big dams. And that's another indication of peak limits around the world. And this is a graph that shows total water withdrawals in the United States from 1900 to 2005, the last year for which we have good good water use data from the US Geological Survey, showing sort of an exponential increase in water withdrawals. This is water withdrawals for everything. Irrigation, power plant cooling, the water you use to flush your toilets and wash your clothes, industrial water use, it's all water use in the United States. Exponential growth as populations grew and our economy grew, and then a leveling off. And in fact, we use less water in the United States today for everything than we did 30 years ago. In many ways, this is peak water limits in the United States. We might want more water out of the Colorado River or some of our other resources or some of our groundwater systems, but we can't have it. And that's a very important dynamic in water these days. So, now is peak renewable water. Peak non-renewable water is, as I've mentioned, the idea that we're also tapping into non-renewable systems. We start to extract water from a non-renewable stock. It increases exponentially, and then all of a sudden, it starts to become more expensive and more difficult. Groundwater levels drop, it's harder and harder to reach, it takes more money and more energy to pump that groundwater out, and our withdrawal rates start to decline because it's no longer economically feasible. That's an example of a peak non-renewable constraint. And we see this with fossil groundwater extraction in the Central Valley of California, in the Ogallala Aquifer in the Great Plains, in Libya, in northern China, and parts of India. Overall, worldwide, by some estimates, 30 to 40% of our global food production comes from non-renewable groundwater. And that's not sustainable in the long run. This is a graph that shows the Ogallala Aquifer under the Great Plains. Just to orient you, here's New Mexico, here's Texas, here's Oklahoma, Kansas. This is really the Great Plains, up to Nebraska. This is one of the major groundwater systems in the United States. It's also an area where we grow a huge amount of soybeans and corn and grains. It's an important food production area. And the red color is over-extraction of groundwater. It's dropping, it's areas where groundwater levels have dropped 40 feet or more, sometimes hundreds of feet, because of over-extraction of groundwater, especially in the southern part of the Ogallala. And that's a non-renewable problem. In parts of this southern part of the Ogallala, farmers are already going out of production because they can no longer afford the energy to pump the groundwater to produce the economic gains that they get from agriculture. The third term is peak ecological water. And this is the idea that eventually we reach a point where the ecological costs of our water use exceed the economic benefits that we get from using that water. The idea is that if the y-axis is the total economic and ecological value of our water use, and the x-axis is the amount of water used, we start to extract water from wherever, and we put it to use. We grow things, we make semiconductors, we get economic value. And the economic value starts to go up. At the same time, we're taking that water out of natural ecosystems. And there's an ecological cost to that. And eventually, we reach a point that we called peak ecological water, where the next unit of water that you take causes more ecological harm than it provides economic benefit. And the value starts to go down. You pass the point of peak ecological water. Now, we're really good at measuring the dollars you can get out of using a gallon of water to grow wheat or to make semiconductors. We're not good at measuring the economic cost of ecological harm. What is the economic loss of extinction, or the loss of a fishery, or the inability to swim in a river that's now so contaminated that we can no longer use it for recreational purposes? There's a true value to that, but we're not good at putting dollar values on it. But that doesn't mean that we're not reaching or passing ecological limits. We are. We're just not good at measuring them. And a good example is the Aral Sea in the former Soviet Union. The Aral Sea is an inland sea. It was fed by two big rivers, the Amudarya and the Syr-Darya. During the Soviet era, those rivers were completely diverted to grow cotton in the Central Asian republics. The Aral Sea started to dry up because the only inflow of water was diverted away for growing cotton. And all 24 species of fish found only in the Aral Sea went extinct. They're gone. Permanently, they're gone. Now, what's the economic value of that? I don't know. But I would say we are long past the point of peak ecological water on systems like the Aral Sea. And there are many, many other examples I could give. That's the issue of peak water. I'm going to talk very briefly about climate change. Even without climate change, we have very serious water resource problems. We have billions of people without access to safe drinking water or adequate sanitation services, which I'm not going to talk about much, but it's one of the biggest water challenges that we face. We have deteriorating natural ecosystems and this problem of peak ecological water. We have deteriorating investment in infrastructure. Many places where we've invested in infrastructure, we're not investing in maintaining and upgrading that infrastructure. And there are parts of the world where we have not adequately invested in water infrastructure. I would say there's little public awareness about water problems. That's changing over time. I think we're moving in the right direction, but there are plenty of people who simply don't even understand that there's a water problem because they turn on the tap every day and fresh water comes out. Incredibly high quality potable water comes out, and that's always the way it's been for them. And they don't see these bigger problems. There's a political issue. We have ongoing disputes and violence over water. I'm going to come back to this a little bit later. We have few coherent international water policies around water, about how to share water resources, about how to share data about water resources, about how to measure many of these things. And at the national level, there are few coherent national water policies as well. Without a doubt, we're changing the climate. I could give a complete separate talk about climate change, and I won't. I'll simply say that there is an incredibly strong consensus in the scientific community that not only are we changing the climate, but not only is the climate changing, but that humans are responsible for climate change. In fact, the scientific evidence is as strong that we're changing the climate as it is that smoking tobacco causes cancer. It's that strong a consensus. And one of the most important impacts of climate change is going to be on water resources. The hydrologic cycle that I've already described is the climate cycle, if you will. As temperatures go up, as dynamics of storm formation and storm frequency and intensity change, we're going to see changes in the demand for water because of higher temperatures. We're going to see changes in precipitation patterns, in extreme events, floods and droughts. We're already seeing rising sea level that's going to have impacts on coastal aquatic ecosystems, freshwater ecosystems, and aquifers. There are many, many connections. I'll touch on some of those in a moment. This is a graph that simply shows the last 2,000 years of temperature anomalies worldwide based on paleoclimatic reconstructions and also based most recently on the temperature, the instrumental temperature record. And so again, climate goes up and down. There's natural variability in the system. Over millions of years, climate has changed because of natural dynamics of climate change. But as you can see, the Industrial Revolution has fundamentally changed things. We have very, very rapid climate change going on now, and it's going to get worse and worse. If you're interested in more detail on this, the scientific summaries of the Intergovernmental Panel on Climate Change, Working Group 1, talks about the science of this. Working Group 2, which was just released a week or two ago, the latest update, talks about impacts. Working Group 3, which is going to be released in the next few weeks or months, talks about policy issues associated with greenhouse gas emissions. But extreme events is a big part of this, and increasingly we are seeing a change in the dynamics of extreme events. This is a satellite photograph of Hurricane Sandy that struck a couple of years ago in October 2012, one of the strongest Atlantic hurricanes on record. Sandy wasn't caused by climate change. That's not the argument. Sandy was influenced by climate change. Sea surface temperatures were unusually warm, and sea surface temperatures affects the strength of hurricanes. And sea level rise was already a couple of inches higher than it would have been because of climate change. And that happened to occur, that's been happening over 100 years, but Sandy happened to occur at a time of high tide when a few inches of additional sea level rise actually had an enormous impact overall. So the influence of climate change on extreme events is a very interesting scientific question right now. There's all sorts of great science being done on that, but we're going to see a growing impact of climate change on these extreme events moving forward. And for water, climate change means earlier spring runoff in a snowmelt-driven system like California, where we get snow in the winter and we get runoff in the spring and the summer. We're going to get higher winter flows because instead of getting snow, we're going to get rain. What we do get as snow is going to melt faster and run off earlier. We're seeing already earlier ice breakup in Arctic rivers. We're seeing a change in the flood and drought frequency and intensity. Evapotranspiration is going up because temperatures are going up. That's going to affect groundwater recharge rates and challenges. We're already seeing massive loss of glaciers worldwide in the Himalayas and the Andes and the Alps and in the glaciers in mountains in the United States, and an increase in spring flows because of faster dynamics of melt and a decrease in summer flows. That's a problem especially for the Himalayas and the mountain rivers that originate in the Himalayas. We're seeing soil moisture drying in areas that are already dry. We're seeing reduced renewable water availability in arid and semi-arid regions. We're seeing impacts on aquatic ecosystems that require those same flows that humans also require. And we're going to see changes in water quality because of higher temperatures and changes in flow dynamics in rivers. And we're going to see all sorts of other things as well. Impacts on desertification, on erosion, wastewater treatment costs, water demand, from the natural hydrology to human managed systems. Climate change is going to have and is already having a wide range of effects. A couple of comments about water and conflict. One of the things we do at the Pacific Institute, which is my institute in Oakland, California, is we look at the issue of conflict over water resources. If you're interested in history, if you're interested in politics, go look at worldwater.org. We maintain something called the Water Conflict Chronology. Google Water Conflict Chronology, it comes right up. This is a database that contains hundreds of entries of conflicts over water worldwide. There's an interactive map, there's a list, there are data references for all of these entries, looking at 4,500 years or longer of conflicts over water resources. We've done a series of studies on these. This is an analysis that looks at the last 80 or so 80 years of entries of water conflicts, split by state-to-state conflicts, that is one nation versus another nation, in blue. And the red lines are, the red data entries are subnational conflicts over water, conflicts between pastoralists and farmers, or upstream water users versus downstream water users, or cities versus farms. Conflicts that start maybe not necessarily for water reasons, but have a water component to them. And one of the things we see is an increase overall in the number of conflicts related to water. Another thing we see is that the vast majority of these conflicts, and a trend in this direction, is not nation-to-nation conflicts, but subnational conflicts. And there's been a lot of discussion in academic circles and in the literature about the ability of nations to deal with conflicts over water resources by developing treaties, by using the tools of diplomacy and negotiation to reduce the risks of conflicts. And I agree with that. But those tools are less well developed for subnational conflicts. And the trend toward increasing subnational conflicts, in my opinion, is a worrisome one. So, what does peak water mean? It doesn't mean that we're going to run out of water. Water is mostly a renewable resource. It does mean that we're going to run up against renewable flow constraints that are a combination of natural and economic limits on the big rivers around the world and the big, even renewable groundwater systems. Where water is non-renewable, we're going to run into stock constraints. And increasingly, in many basins around the world, we're running into peak ecological constraints as well. And all of those dynamics complicate water management. I'd also argue that we have to integrate climate change into these challenges. The assumption for water management is the future climate's going to look like the past climate. That's how we design our water systems, that the frequency of droughts and the frequency of floods that we've experienced over the last instrumental record, whatever we have, is going to be repeated in the future. And that is no longer the case as well. So that means we have to think differently. I'm just going to talk for a couple of minutes about some solutions, and then I'm going to turn this over to Jay. I think there are solutions out there to our water problems. I think we're moving in the right direction, slowly, too slowly, but slowly. At the Institute, we talk about what I call the soft path for water, an alternative vision for how we manage our water resources, and there are a series of components to that. One of them is we have to rethink the issue of supply. We're not going to solve our water problems by building more big dams and reservoirs. We need to build some new dams and reservoirs, some new traditional infrastructure in some places, but that's not going to be the solution to our problem. The traditional supply option is running into limits. Limits on our water resources in our rivers, limits on our groundwater systems, and those limits are natural resource constraint limits. And there are limits to the ability to get around that problem. But there are new supply options. We could, for example, use treated wastewater for all sorts of things. We spend a lot of money in the developed world collecting wastewater and treating it sometimes to a very high standard, and then typically throwing it away. That's a supply option. We could desalinate water. 97% of the water on the planet is salt water. It's too salty to drink, it's too salty to use to grow crops, but we know how to desalinate water. And we desalinate water in many parts of the world. It's extremely expensive, economically. But as we run into these other constraints, we're going to have to be willing to pay the price for more and more expensive sources of supply. As we start to integrate ecological issues into our water management decisions, water is going to become more expensive. So there are supply options out there, but they're not necessarily the cheap, easy access water of the past. We also have to rethink the concept of demand, however. We don't want to use water except for the most basic things, for drinking, for survival. We want goods and services. We want semiconductors. We want to grow food. We want clean clothes. We want things that water use helps us provide. But if we can do the things that we want with less water, that's the question of demand. If we can grow more food with less water, if we can wash our clothes with less water, if we can deal with human waste with less water, we can do the things we want with less impact on our natural systems. And that's the issue of demand management, it's the issue of productivity and efficiency, and it's the other side of the supply-demand equation. I showed you the graph of total water withdrawals in the United States that grew exponentially and then leveled off. Our economy has continued to grow exponentially. Our population has continued to grow exponentially, but our water demand isn't growing exponentially. The fact that our water use has leveled off hasn't meant that our population is suffering. It hasn't meant that our economy is suffering. We're getting smarter at how we use water. And that's the demand side of the equation. There are other things going on with that curve that we maybe can talk about later, but it's an important point to think about. We also need to protect water quality and match the quality of supply to the quality of demand. I mentioned treated wastewater. We could treat wastewater to a potable standard and use it for potable drinking water. But a lot of our water demand isn't potable. It's for power plant cooling, or for irrigation, or for watering our landscapes, or for flushing our toilets. We don't need potable water for everything. If we match the quality of the water we have with the quality of the water we need, that's a solution to our problems as well, and it opens up all sorts of alternatives. So supply, rethinking demand, rethinking water quality are all components of the soft path for water. We have to use smarter economics. Often we don't price water properly. Often water is too cheap, and that encourages waste. It encourages inefficient use. If we're smarter about economics, then we're going to be smarter about water management. We have to fundamentally protect ecosystems. The day when you could build a big dam on a river and you didn't care about the aquatic ecosystems in the river or downstream or over, where they ought to be over. So thinking about integrating ecosystem protection into our demand for water is a new part of water management as well. And we have to improve water institutions and management and public participation. Again, in the old days, water management was engineers mostly, and men mostly, and no discussion in local communities about upstream water management or about what's going on downstream. We have to think about smart management in a much more democratic, much more open community way, and that's part of a soft path for water as well. So we can break the link between demand for water and our economy, our economic growth, that exponential growth that we'd like to see in our economy, and growing populations, but it's going to require new thinking about water. And I think we can move in that direction, but we're not. So the water problem is real, it's complicated. In many parts of the world it's bad, depending on which piece of the challenge you want to look at. There are economic, human, and environmental costs to doing nothing, especially in the face of climate change, which is a new challenge for us. And new thinking is needed. We need solutions that are sustainable, scalable, socially responsible. We need new technology or better application of old technology. We need better and smarter economics, and we need smarter and more integrated institutions. I think we're moving in the right direction. We have to think about how to move in that direction faster. There are lots of different pieces to this puzzle. We do a lot of work at the Institute on water, on desalination, on efficiency, on management, on economics, on ecosystems, on conflict. My email's here, our website's here, and I look forward to the conversation. Thank you very much.
All right, thank you so much. Gosh, this must be hard, two back-to-back presentations. Do you want to get up and stretch or something, or are you okay? Good. All right, so here's the challenge. The challenge to you folks is to think laterally between the presentations that Dr. Gleick just gave and that I'm about to give, because there is some very interesting overlap. So please pay attention. And I'll do the same. I try to point some of it out to you. So I want to talk about some of the research that we've been doing. Gosh, is it already 20 years? It goes back almost 20 years now, using satellites to track freshwater availability around the world. And primarily we use a NASA satellite mission called GRACE, or Gravity Recovery and Climate Experiment. We started before the mission launched. It launched in 2002. We actually started back in about 1995, did some pre-launch studies to explore feasibility. Where do I point, or does this do this? This, okay. So these are the things that I'll talk about. So we'll talk about water cycle change, and we use the term in hydrology and climate of quite a bit of water cycle intensification or more energetic water cycles. So we'll define what those things mean. I'll show you some brief examples of, I'll talk about the GRACE mission, but then show you some examples of how we're kind of getting at, are we seeing some of these things happen? Are we seeing things like, what are we seeing with respect to this strengthening of the water cycle from GRACE? So we'll talk about that. Then, as Peter mentioned, I'll spend a little bit of time talking about groundwater storage and groundwater storage changes in the United States and around the world, and then some implications. And since we're in a school of public policy, there are implications for policy, like Dr. Gleick spoke about, but also implications for scientific communication. Who was at the movie last night, besides the two of us? Okay, so there was a recurring theme in that movie from some of the scientists, and it was, boy, I see something here, and it's pretty compelling, and I need to tell somebody about it. And I said it, and Aaron Brockovich said it, and Tyrone Hayes said it. We also, in a strange way, also mentioned our parents. Like, well, that's not the way my parents raised me, so I really need to go tell somebody about this. And so the implications that I'll talk about are really focused on the responsibility of those of us who do research to communicate. And it's kind of a challenge because in academics we're not rewarded for it. There's no reward system at all. So it's a little strange. All right, so let us look at what I mean by water cycle change, and then the GRACE mission. So when we talk about climate change, really a lot of times when we're thinking about some of the impacts of climate change, a lot of it really has to do with the water cycle. So for example, in a warming climate, a warmer atmosphere can hold more moisture. So as the climate warms, we can expect more evaporation. What goes up must come down. So we can expect more precipitation, and then on land, perhaps that's going to be more runoff globally. So perhaps we should be expecting bigger exchanges or more cycling of water moving through the water cycle again, just like you learned about this semester, but hopefully you learned about it in elementary school as well. The next thing is an increase in the magnitude and the frequency of the extremes of flooding and drought. So this is another thing we hear about quite a bit, and perhaps you're already experiencing. Dr. Gleick mentioned Hurricane Sandy and the ties to climate change, and perhaps that means that we'll be seeing more extremes. And then the third thing that I'll focus on is the redistribution of precipitation from the mid-latitudes to the high and low latitudes, from the arid and semi-arid parts of the world to the wetter parts of the world. So the wet area is getting wetter, the dry area is getting drier. So these three things together, the more water cycling through the water cycle, more extremes, and dry areas getting drier, wet areas getting wetter. Collectively, that's when I talk about water cycle intensification or acceleration or change, because we're seeing that it's sometimes speeding up, it's sometimes slowing down. And what I'm working on is metrics to track that. And like Dr. Gleick said, the news isn't always good, but there are things that we can do. So here's the GRACE mission, and you can see from the inset photo here that the satellites themselves are not very big. Their orbit is they're up about 400 kilometers in the atmosphere, and they're separated by 200 kilometers. They follow each other around in a tandem orbit, and as they fly around, really GRACE functions like a scale in the sky. So the way it works is that these two satellites follow each other around, and say here we are looking at the Appalachian Mountains. So they're flying over the mountains, and anything that has something that has more mass exerts a greater gravitational attraction. So say we fly over the mountains in October, the satellites fly over, they get pulled down, right, because of there's more mass on the ground because of the mountains, they get pulled down towards the mountains, the distance between them changes a little bit, they pass the mountains and they go back up into their original position in their orbit, okay? Now, suppose we fly over the mountains in January after there's been a big snowstorm. Water is extremely heavy. The mountains now weigh more, they exert a greater gravitational attraction, and so the satellites get pulled down more. Their position now is lower than it was in October, or whatever month I said before the snowstorm. Right? So by keeping track of that position of the satellites, we're actually making a direct measure of the water mass change all over the Earth, but we'll just talk about the continents today. So we can really track the weight differences that are associated with the inflows and outflows of water in a region, say because of a big snowstorm, or because of a big flood, or because of something like groundwater depletion. And it's really not that much different than when you think about how a bathroom scale works. It's really the same principle. You get on the scale today, and gravity, right? The force of gravity pulls you, Earth's gravity pulls you towards the surface, and you're crushing, right? You're changing the position of the top of the scale. And so say you've had a long winter and you've eaten a lot of food, and then you get on the scale and you're 10, 15 pounds heavier, you crush that scale, right? You depress it a little bit more. It's essentially the same. The mission was launched in 2002. By all accounts, it should be dead. It was planned for a 5-year lifetime, but it's still going. We don't get 12 months of data now. We get about 9 months. We're trying to save battery life. And there is a follow-on mission that is currently scheduled for launch in 2017. So hopefully we won't have much of a data gap, if any. And let's see, what else can I tell you about GRACE? It's a fairly low resolution, coarse resolution instrument. It works at large scales, regions that are 200,000 square kilometers or greater. I should know how big that is, say, relative to New England, but I don't. It's about the size of Illinois. It's about the size of Southern California. So it's probably about the size of a good chunk of New England. It works on a monthly basis. It takes about a month to make a good map of the gravity field, and really what we're looking at is a difference between, say, 2 months gravity field. So we look at that mass change. And it has an accuracy of about 1.5 centimeters. That means that the storage change would have to be greater than 1.5 centimeters of water spread over this 200,000 square kilometer region. So it actually turns out to be about a couple of cubic kilometers. So the change has to be bigger than that to be detected. So it is not a weather satellite. It's not going to tell us the surface wetness conditions in Boston Common tomorrow. But it is going to tell us how the whole sort of water availability, water status of a big chunk of, I don't know, maybe it's the Connecticut River Basin that's a good size, or appropriate size. It will tell us how the moisture status, the overall water health of that river basin is doing on a monthly and longer basis. So here's what the gravity field, our knowledge of the gravity field before the GRACE mission launched. So this is about 2001, and this was pieced together from different satellite missions, from data on the ground. And you see that it's fairly coarse, but you can see the basic features, the basic tectonic and topographic features of the Earth. But after only 1 year of GRACE data, that's what we ended up with, right? So we went from this to this. So you can see that we're able to, with just a few hundred days of GRACE data, really able to sharpen up our understanding of the gravity field. And really what we're doing is making one of these every month. We've been making one every month since 2002. So we understand the long-term average quite well, and we have gotten quite good at estimating those monthly changes. So, to review, the difference between two of these global gravity fields gives us what we call the time variable component. Right? The gravity field has two components. The static one that's based on the continents are there, the mountains are there, and they change on geological timescales, not human timescales. And time variable component, which is the stuff that changes. And in this case, on the time scales that we're making these measurements, the number one thing that's moving around the Earth is water. The reason that we can detect the movements from these satellites, that the movement of water can actually perturb, right, can pull down those satellites, is that water is exceptionally heavy. In the movie, at the end of the movie, at a couple of points, I think at points when Dr. Gleick was speaking, we saw women in Africa, right, filling up the water jugs and carrying them back to their village. Has anyone ever tried that? Ever tried to fill up one of those jugs, like a 5-gallon jug? Who knows how much that weighs?
40.
I know you know. It's 40 pounds. Try putting one of those on your head. Right? Try carrying 2 of those and see how far you can get. Right? So water is exceptionally heavy. And again, right, the people in the we go to Costco and we buy a case of bottled water. You know, when you're carrying it to the car, when you're carrying it from the car into your house. I don't do that anymore, okay? But you know how heavy it is. So what we're seeing from GRACE on land is gravity changes that we see from GRACE are really dominated by water storage changes on land. GRACE tells us, if you look in the upper right, imagine this is a big watershed that's greater than 200,000 square kilometers. Okay? GRACE tells us the change in the total amount of all of that water, all of the snow, all of the surface water, all of the soil moisture, groundwater together on a monthly basis. Okay? If we want to figure out how much of it is groundwater, break up that GRACE signal into its pieces, we need other data. Some of it can come from satellites, some of it can come from data on the ground, some of it can come from computer models when all else fails. And one of the things we get out is the time series like that shown in the lower right. And this is the time series for the Colorado River Basin going back to about 2004. And you see that there's a long-term decline there that we're quite familiar with in the western U.S. So those are monthly data, right? So they're showing you the ups and downs of the total amount of water storage for the Colorado River Basin. And storage is going to go up when there's more precipitation and snow, and it's going to go down when there's more stream flow out of the region in the dry season, right? There's more evaporation. So those are ups and downs. And there's a long-term decline, which in this case actually has to do with groundwater depletion. And I've already mentioned the space-time limits. So again, these are what some of the data look like, and this might be a good opportunity to tie into some of Dr. Gleick's comments. So this is a map that was published in last June, so June 2013. So it's GRACE data for the United States, and it's a map of the trends in freshwater storage. Okay, so blue places are gaining water, red places are losing water, and then the time series, those charts correspond to the different numbers, the Central Valley, the southern part of the Ogallala Aquifer, all across the southeastern U.S., and then the big wet spot in upper Missouri. So we see a couple of things when we look at this figure. It's a pretty stratified country, at least in this GRACE time period. We see that the upper half of the country is getting wetter and the lower half is getting drier. And then we see these embedded hotspots, which correspond to some things that we know pretty well, like the Central Valley Aquifer, right? Like the pipelines or the southern part of the Ogallala Aquifer. The southeastern U.S. is paying attention to what, and a lot of us don't really know what's happening in the southeast, but if you're in the southeast, you know that they're actually having conflict. I don't know that it's armed conflict, but they're having what they call their regional water wars. It's very dry, okay, and there's a lot of groundwater depletion. we can get back, maybe in the discussion we can talk a bit about the peak water thing. But one of the points that I want to make now, and think about it, maybe we can talk about it in the discussion, is Dr. Gleick says, maybe we can reach that peak renewable water, right? And when we've reached peak renewable water, and we need more water, the first obvious choice is to use groundwater. And so that, in a sense, is why we're seeing these red spots, okay? Because we're using more, right? And it's there's loss of water there. We're using more water than is coming back, right? That's being replaced. So we're mining water in many cases it's groundwater. So we can come back to that. So this just shows what some of these charts look like for the whole world, right? So we can take these data, and what I'm trying to convey is that we can make maps. I just showed you the U.S. map. I'll show you a global map, so we can look at long-term trends, or we can look at charts of the monthly time series, like the monthly ups and downs, and we can do it for any shape region we want. We can do it for aquifers. Here's some river basins, and we can start to see these ups and downs of water storage that we had never been able to see before. It's really, really difficult. Hydrology, given the importance of water, hydrology is actually quite data limited. It's very difficult to put together a comprehensive data set, say in a big river basin or an aquifer, of what the groundwater levels are, what the levels of moisture in the soil are, how much snow there's been, what are the stream flows. Some of those things we measure, and some of those things we don't. In the US, we're in great shape, okay? But when we start doing things internationally, it's a completely different picture. So satellites like this and other satellite issues really help us get around what I call the data denial, this issue that other countries won't share data with you for some good and some bad reasons. Sometimes they're political, but sometimes they're security reasons, they're economic reasons. There's issues, often issues of economic security. You don't necessarily want your neighbors to know what the flow rates are because they might send fishing boats over to, fish in the region. On the other hand, you might not want them to know how much groundwater you're using. So I've always felt that these data can be important in transboundary water issues, and I hope that proves to be the case as time goes on. All right, so what are we seeing with some of our research on water cycle change? Well, here's a chart that shows. So I'll go through the three examples of: are we seeing more water moving through the water cycle, or how might we get at evaluating that question? Are we seeing changes in the extremes? Are we seeing more extremes? And how might we get at that with some of these data? And are we seeing the wet areas get wetter and the dry areas getting drier? So this is a chart that, so I mentioned in one of my first points, that if the water cycle is getting stronger, one indication might be if we're going to have more precipitation globally now, and more evaporation, then on land maybe we'll see more runoff, okay? More stream flow. Okay? The problem, the scientific problem, or the measurement problem, it's both technical and scientific, is that we don't gauge all of our rivers. Okay? And we gauge a lot of the big ones, but getting back to my data sharing point, it's really, really difficult. In fact, it's impossible to put together a global data set of stream flow from the world's rivers. Can't do it. Say in near real time, on a monthly basis. If I want to put together a data set, say for the last 10 years, on a monthly basis of global river flows, you can't do it. Okay? So what we did in this study is it's a little bit unusual for hydrology. What we actually did was do a water balance, a mass balance. It's all based on remote sensing. A mass balance on the ocean. Okay? And what we did is you do a mass balance of change in storage is equal to the inflows and outflows. You get change in storage from GRACE and from some other data from some other satellites, if we want to go back before 2002, when GRACE launched. So we get the change in storage from GRACE and other satellites. And then the inflows and outflows into the ocean. So inflows are precipitation, which we can measure from satellites, and river discharge, which we don't know globally. And then the biggest outflow is evaporation, which we can get from satellites. So we have 3 of the 4 unknowns. We've got the change in storage, we've got the precipitation, we've got the evaporation, and we measure the river discharge. And that's what this chart shows here. It goes back to 1993 or so, using some sea level data, and that's the black curve, and it shows an overall increase. So you see the intraradial variations in global river flows. And then the red line is the more recent estimate that we did using the GRACE data. So it starts in about 2002, 2003. And bottom line is we see an increase in river discharge. We see an increase of about 1.5% to 2% per year, which is actually a lot. Right? It doesn't sound like much, but when you start thinking about decades, it gets to be a lot. Does it mean that the water cycle is accelerating? Maybe. There's a lot of intraannual variability there. Maybe more important is that we've figured out another complementary way to do this, and we can track this over time. So we have 20 years of GRACE data, or maybe 30 years of GRACE data, because there's another mission planned for 2025. We can track this stuff over time. Okay, are the extremes changing? Are we seeing more extremes? And we get at this in a couple of ways. One, this is a new paper actually, and what I show on the top is the GRACE data, the ups and downs of all water storage in California. It's really the Sacramento-San Joaquin River Basin. It's a big chunk of the middle of California, where Central Valley is. We grow all of our food, and we get most of our water from there in the Sierras. So it shows the ups and downs. So the middle is, now that we have the data that we see here in the top panel, the middle, so now that we see what the monthly variations are, we can start to get a handle on what the average variations are, right? What are the average ups and downs? What's the average annual cycle of water storage, right? So we never had the data on the top, so we never knew what the data should look like in the middle, the average. It's like, checking your blood pressure every day and charting it out, right? And you do it for 10 years, and so you see the variations and the swings, but you also know what the normal range is. So the middle is the normal range, at least for this GRACE time period, and the top is actually what happened. So that you can see quantitatively what the deviations are in wet periods, how much wetter, say, is, there we go. So how much wetter is this period from the normal wet conditions? How much drier are these low points from the normal dry conditions? And so we plotted out, because California is in such a big drought, we plotted it out here on the bottom. And you can see a few things. Now it's a short time period, and you can see that the severity, right? What the size of the green of the green data there, right? Show the actual quantitative magnitude of the drought. It's saying basically here. So we're right about here right now, right? So we can say quantitatively we are 25 cubic kilometers below normal dry conditions. So if you're a water manager, that gives you a bit of a target, right? Oh, okay, because people always ask the question, if it rains, are we out of the drought yet? I don't know. And we have to do more than just check the reservoir level. So this allows us to say, hey, we're at 25 cubic kilometers below normal wetness conditions. So we need this much more precipitation, and maybe we need to do this much more recycling or desal or conservation. It gives us a number. The other thing that we can see pretty clearly is the beginning and the end of a deficit period or drought period. So we will be tracking this over time, and we do it for both the wet and for the dry. So we published a paper on flooding in 2009, and this one has just come out in geophysical research letters on drought. So we can keep track of this, and over time, we can start to characterize the frequency and how it's changing. So it's not the answer, but it's like a cool, I think, new tool. Okay, now how about these variations, the increasing extremes? Let me go back here for a second. When we look at these time series, right, I mentioned before they go up, right? So this is really representing the change in storage. So the change in storage will go up when the inflows are greater. There's more precipitation, more snow coming into a region, and they go down right? When there's more evaporation, okay, more river discharge, okay? And so if the water cycle is getting stronger, if there's more precipitation, and then there's more evaporation, that amplitude, that peak to peak height may be changing. Now we can measure it, right? We can start to measure it. And so that's another thing that we've been working on. This is a map of the amplitude, the peak to peak height. If we made some of these charts for every point on this map, that's what this map is. Okay, it shows us the amplitude or the strength of the water cycle. And it looks like the gray and pink colors are stronger water cycle. That makes sense. It's the tropics, right? As you move into the arid and semi-arid regions, there's less happening, at least on the precipitation side. And so we get this sort of poleward decrease. The other thing we can do is track how this amplitude changes over time, right? Because if amplitude is changing over time, that's really, we're saying the strength is changing over time. So it's a measure of this acceleration of the water cycle. And graphically, you can see it here. This is a chart from the Amazon, the storage changes in the Amazon. So you can see pretty clearly, right, that amplitude is getting bigger over time. So you know, this is still work in progress. In fact, I'm going to Taiwan next week on Saturday to try to finish this study. Part of what we're going to do is map out where this amplitude is changing. And here's a first figure that kind of looks like that. Looks at what's happening globally. So the blue places are places where the water cycle is strengthening over the last decade or so. You know, the big player is really the Amazon, and it's such an important watershed for hydrology, for climate, for driving sea level variations. It is really the workhorse of land hydrology. So it's a big player, and we'll be doing some more research on that. Are we seeing the wet areas get wetter and the dry areas get drier? This is a well-known plot from the IPCC. This is AR4, which is the last report, and it's a pretty well-known figure that shows precipitation changes by the end of the century in the winter on the left and summer on the right. The blue areas are places where precipitation is increasing, and the red are places where precipitation is decreasing by the end of the 21st century. So we see this we call it mid-latitude drying. And so what are we seeing in the GRACE data? So here's a global figure. I showed you the US figure before. So here's a global figure. Again, the blues are gaining water and the reds are losing water. So I'm going to pose the question to you, and I'm going to try to lead you to the answer that I want you to give me. Are we seeing this redistribution already? And maybe we are, maybe we're not. We've done some more work on this. There's this, you know, statistically, when we look at the trends by latitude, it's statistically significant for sure. And so that picture really stands out. But it's only 10 years of data. So again, we have to keep looking at these data, keep updating these studies, keep an eye on this stuff.
Greenland.
We will talk about I'll get to that. So I want to talk about what those spots are, and I'll get back to that in one of my last slides. The biggest signals are the ice sheets. So now about groundwater depletion, and getting back to really the peak water thing, and what do you do when you've used up all the flows? Well, the answer is when you use up all the flows, again, one of the most obvious things that we do is hit the stocks, hit the groundwater, the non-renewable part. And so that's a huge concern for water management. So let me show you what. We've been throwing around the term groundwater without really saying what it is, or really describing its importance. First of all, groundwater is that water that's stored under the ground, right? When we talk about surface water, we're talking about rivers and water stored in reservoirs and lakes and snow and ice, the stuff that you can see. Groundwater is basically the stuff that you can't see. And in particular, as we go down into the soils and the soil pores get saturated, we hit what's called the water table. Right, so groundwater is the water that's stored in soils, in aquifers, which are soil and rock units that can store significant amounts of water in their pore spaces. It's a huge amount of water. It's most of the water. right? We really were super focused on surface water because it's available, it's accessible, we see it, you know, sort of the evolution of humanity has been to use what's available, what's readily accessible first, and then move to the more challenging, difficult to access stuff. In this case, it's groundwater. So it accounts for most of the fresh water. It's the major source of water for over 2 billion people. It supplies about 45% of water for irrigation globally, half of the drinking water of the United States, 60% of the water used for irrigation. So you can see right away, it's incredibly important. It is the strategic reserve in times of extreme drought. And unfortunately, groundwater withdrawals go unmonitored and unmanaged in many places around the world, including the United States and especially in California. And the lack of management, I think, is really becoming apparent when you look at that US figure that I showed, right? That has all those red hotspots. So a goal of ours has to be maybe to take those hotspots and change the color from, you know, from red to more of a blue color. That is, by the way, what's happening in what's happening locally. Happens locally in Orange County through recycling of sewage water, which we can talk about. Also, countries like Israel are doing a great job of actually managing and monitoring their groundwater very, very carefully, so they keep that trend from going down. You know, they've had a decrease, and now they have made it level off. All right, so I mentioned before that if we wanted to use these satellites to estimate groundwater storage changes, Grace tells us the total change in this river basin. Grace is telling us everything, all of the change. If we want to focus on the blue, this change in the groundwater, we have to get data on the soil moisture and the snow and the surface water storage and basically subtract it, right? That's what these, here's a mass balance based on our stocks. The total storage, or change in total storage, is the snow, the surface water, the soil moisture, the groundwater. If we want to solve for the groundwater, here's our Grace data. We need data on snow, surface water, soil moisture. We get it. You know, if we're trying to do a study in the Middle East or in India where we have no access to data, we try to use other satellites. We use computer models. If we do a study here in the United States, we've got a lot of data, and we use mostly observation. Here's a few studies that we've done that have looked at groundwater depletion from top to bottom. California and the Central Valley, and in the middle is the Middle East, and on the bottom is India. The colors are going from sort of a wetter period. All of these studies were 2002, 2010 or so time period. And so the green colors mean it's a little bit wetter at the beginning of the study, and the red colors mean it's a little bit drier. And on the right, we go through that exercise of getting the data on the snow and the surface water and the soil moisture, subtract it from Grace, and we solve this mass balance on the stocks or the storages for a groundwater storage change, right? And so we see the ups and downs, but some long-term trends shown here. I guess in all cases it's a blue line, and we can see the relative rates of groundwater depletion. To put it in perspective, 18 cubic kilometers per year for India. This was a study that was published in 2009. This is the place where we have the strongest rates, the biggest rates of groundwater depletion are happening in India. Number 2 is actually the Middle East. Okay? The Central Valley, although it's quite significant for us, from a global perspective, it's not as bad as many other places. So anyway, this is work in progress. Now, the global situation is one, like Peter said, it's real and it's bad. And this figure, let's spend a little bit, so it's the same global figure I showed you before, but it has some of these trends labeled. So if we look at the places that are losing water, the biggest signals are the ice sheets, right? So Greenland and Antarctica, and of course, they are melting away, and the main drivers behind sea level rise. Sea level is rising at about 3 millimeters per year. The next biggest signals are actually the glacial melt. So Alaska, and the biggest signals in these data are actually Alaska and Patagonia. Some of our newer data, the Peruvian glaciers are starting to show up, and then of course there's the glaciers melting around the Himalayas. A lot of those other red spots in red colors are due to groundwater depletion, or groundwater depletion coupled with drought, because when there's a drought, we use more groundwater. And so just about every red spot sits over a major water source, a major aquifer. Pilbara region here in northwestern Australia, we've often felt this is probably due to the water use for mining, mineral mining. The North China Plain, that India signal now stretches wide across India and Bangladesh. Middle East, the Aral Sea region, the Guarani Aquifer, I always have difficulty saying that, down in South America. And then I showed you already a more detailed map of the United States. Okay, and so what we find when we look at the different aquifers and the major aquifers in the semi-arid and arid parts of the world in this Gray's time period is that they're all undergoing significant depletion. Okay? So this is a problem because it's our strategic reserve, because we're maybe maxed out on the peak water, the peak renewable water, right? And maybe we've maxed out on the peak groundwater, but we're certainly depleting it, and that's why those red spots are there. Okay? So we have to get a grip on what to do about this within our country, within our states, and then internationally is much more of a challenge. So to the implications, this is so we're having a drought. I'll just put this in the context of what's happening in California. Really, really bad drought. Okay, this is a political cartoon that was in the LA Times. There was a lot of pressure on the governor, that's Governor Brown here, to actually declare a drought emergency. And a drought emergency is different than a drought. So, obviously there's a drought going on, but so a lot of the discussion was, well, how come, is the governor God? How is it that he can determine whether or not there's a drought? Really, what he declared was a drought emergency, which makes some federal funding and water transfers and some water management issues a little bit easier. So it's a bad situation. I want to show you. We declare a drought emergency, and national news about the drought, about drought relief from President Obama. A couple of important things have happened, and so we move water all over the place in California. The biggest source of water is the mountains. The biggest renewable source of water is the snow in the mountains. Okay, so that water drains essentially into reservoirs from the Sierras, drains into the Sacramento, San Joaquin River basins, flows into the Delta, and then we put it in these crazy aqueducts and we move it into the Central Valley to support agriculture and down to Southern California, so people like me can live down there. The amount of water that is allocated, that's put in to the aqueducts to support farming and to support domestic and municipal needs in say, Southern California, that varies. It's a political decision. So there are allocations that are announced every year. And so this year, and there's two main aqueducts or projects. We call one the State Water Project, the other one the Central Valley Project. Long story short, both those allocations were zero this year. And so no surface water. It doesn't really mean that there was no surface water available, but for all practical purposes, those allocations were cut to zero, right? So if you don't have any, so the president was there, again, you don't have any surface water, one of the first things you're going to do, well, of course we should conserve, but one of the first things you're going to do, especially if you're a farmer and you want to grow that food, and we do need to eat, is that you're going to hit the groundwater pretty hard. So let me just explain what we're seeing from Grace. So this is the total water storage, the Grace data for the Sacramento, San Joaquin River basins, the big fat part, middle part of California. Again, showing the ups and downs of water storage. I want to just point out a few things that are, for Californians, are maybe less apparent. Maybe this will be new information for you. First of all, okay, this is sort of November, December 2013. It's the lowest point in the time series. Okay, that's good because that's consistent with our longer term understanding of how things have changed in California. Second point is, that's an awful big decline there over the last couple of years. And the rate of decline is about over 10 cubic kilometers per year, which is more water that all humans use on an annual basis, the domestic and municipal water use, is about 10 cubic kilometers in California. That's, just to put it in perspective, that's how much water we've lost for the last couple of years. Third thing is, we tend to say in California that this has been a drought that's been going on for a year, maybe 2 years, right? Because we're always looking sort of relative to this last relatively wet year. But when I look at this figure, at least in this time period, I don't have a big problem saying, you know, maybe the whole thing is an overall long-term decline, at least back to about 2005, 2006. Maybe we've been in continuous decline with the exception of a couple of wet years. Again, you know, we can play all kinds of games with longer time series and trends and so on. But new information, and I think it's borne out when we look at that U.S. map that I showed you as well. There's information here on the integrated water health of these river basins and aquifers that we're not really using enough. I think it gives us a little bit better, more holistic picture of the water status of our river basins and aquifers. All right, so this is the total, right? And of this, how much is groundwater? What's happening with the groundwater? How have we updated our groundwater plots in recent years? The black line is our groundwater, and forget the red and the blue for just a second, okay? And so what we're seeing here, so when we published our study in 2011, we basically went from about 2003 to about here, 2009, 2010. So this is consistent to here with what we saw before, and now we're up here. So we've recovered a little bit, and here we are now. We're over here right now, okay? Now, let's consider what these black and the red and the blue lines mean, or red and blue bars. Those are the surface water allocations, okay? That's the surface water that's available to the farmers, okay? So I was kind of surprised at how this figure turned out. But there's pretty much a one-to-one relationship. When surface water availability, when the bar is bigger, that means the allocation was bigger. There's more surface water available for the farmers. Okay? When surface water availability increases, groundwater recovers. When surface water availability declines, groundwater declines. Okay, it's not rocket science, but you know, it's a pretty nice graphic, I think. Then we've had some bigger allocations, and the groundwater has recovered a little bit. But really, this is where we are right now. So this is the reason for concern, because the drought is worse than ever, and the allocations are zero for the first time. So the thing that I have been sort of waving the flag about is, where are we going to go? I mean, are we going to go through another huge phase of depletion? How long can we do this? How much groundwater do we have? How is its quality changing? We need to get some of this. We need to get our acts together on managing our groundwater. Maybe this puts it in a little better perspective as well. This is a longer-term picture of groundwater depletion in the Central Valley, and it's a combination of USGS data shown in red and the Gleick's data shown in green. And it goes back to about 1962, and it just shows the cumulative water loss, cumulative depletion in the Central Valley. And the colors in the back represent the climate. The wet periods are the dark blue, the white color are the droughts, okay? And the lighter colors are sort of variably wet to variably dry. So one thing I think that's pretty clear in this figure is that our history is one of a little recovery in wet periods, and then big decline in drought. Little recovery, big decline. Little recovery, decline, right? Here we are now, and again, put that rotating, whoops, I'm supposed to have a rotating question mark there, but like I said, it got left off. Same thing, right? Given that we've had these big declines in past droughts, okay, I raised the question or the concern of where are we headed now, given that the drought is worse than ever and our surface water availability is less than ever. How long can we keep doing this? Where are we going to go? Where are we going to end up, right? And so to tie it to what Peter was talking about, you know, we don't know in terms of our peak groundwater when we're going to level out, right? We don't really know, but we do know that as we go deeper into the aquifer, the pumping costs are greater. It costs more money to dig deeper wells. The water quality is decreasing, right? And these are all things that we don't really measure that well. So anyway, big concern there. Now, what should we be doing about it? Just a couple of slides. I guess the most important point that I want to make is the one that I made earlier, that for those of us that are in academics, there is not a lot of encouragement to talk to the public, to communicate. I write occasional op-eds and do some blog posts and really try to communicate the things that we do, the things that we're finding, as well as do things like teacher training and K through 12 education. Because I think that we all need to work together, and I'm clearly quite concerned about getting the message out. My encouragement to faculty and to research scientists is to really try to communicate those key results to your elected officials, to your environmental decision makers. Do the public talks, do the professional talks. I've been giving talks to, at fracking conferences, just to talk about the things that we just talked about. Students, thanks so much for devoting yourselves to the environment. I think a big take-home message here for students here is to really hone your oral and your written communication skills. You must have your soundbite. You absolutely have to be able to tell the taxi driver, right, or I don't know, is the T automatically driven now? They actually have drivers on the subways, whatever.
You can't talk to them.
Tell the man on the street, okay, have your soundbite. This is what I do. This is why it's important. I think all of us have to try to help educate the general public. Social media has been great. Follow us on Twitter. We follow each other, and we'll follow you. Please follow us. Something I talked about last night. I do think that we need to raise awareness as a community of critical water issues to the level of everyday understanding. Other communities do it. We've kind of lagged behind in water. We have to work together to get the message out. Because the thing that I said last night is I think that if we can educate people to understand where their water comes from, question, where does your water come from? Right here, if we go to the water fountain, we go to the faucet in the men's room, what is the source of that water? Who knows? I do not know. So 100% surface water? Interesting. Okay. So suppose that there were a drought and the water level started falling. Would there be another supply? Is there groundwater that can be tapped?
Connecticut River.
Connecticut River? Just put a big straw in there?
Some of it is already diverted, I think.
Oh, so there's some diversions. Okay. So this is what I mean. Once you know what your sources of water are, maybe there's quality issues, right? Once you know where your water sources are, you can understand, in our case, right, the snowpack is disappearing in the Colorado River Basin, and we'll be getting more liquid precipitation, less solid precipitation, overall less rainfall. We get a lot of water from groundwater. We're getting about 70% of our water in California right now is coming from groundwater, okay? So once you know your sources and how they're changing over time, then it's much easier for us to accept the need for more attention that water deserves. Some of the things that Peter talked about with pricing and policy, these are critical things. One last thing before I close, and I think we're just saying a lot of the same things but in different ways. One of the things I think that we need to do when it comes to thinking about the future of water management or water policy, we need to change the conversation. In California, it's like, the farmers versus the fish. It's that damn delta smelt, right? An endangered species that's really an indicator species of the ecological health of the delta, that's become the focus of the ire of the farmers. We need to change that conversation from, rural versus urban, man versus fish, to the fact that we need to eat, right? We need to grow food. We need energy, right? It takes water to produce energy. We need municipal, right? We have municipal water needs. We want to grow. We want to grow the economy. So industry needs water, and the environment needs water, right? And we have to recognize that we want all these things. The lights are on, right? We're sitting in a beautiful room, we're using computers, all these things require water. So we have to work on how to, I call it optimal allocation. So from my perspective, we work on, in our group, we work on tools, computer models to help us sort of look at scenarios and what the trade-offs are. This is very, very challenging because, as Peter said, the ecological impacts are undervalued, the environmental impacts are undervalued, we don't price water correctly, and then from my perspective, we have a lot of work to do on the models. But I think that's a big part of the future, is thinking about, we want to do all these things, and we need to work, you as students, and Peter and I as scientists and communicators, need to get that message out that we want to do all these things, and we have to figure out, we want to move away from them being purely political decisions and try to get some science and good information and some data behind how it is we can make better choices.
Institutions in the Global South have a tendency to devolve a lot of power to communities, power as well as responsibility to communities to do a lot of this management. Whereas the Global North has generally stuck to a more state-centric sort of pattern of management. And if you look at the conflict map that Dr. Gleick pulled up earlier, you see the Global North actually has a lot of conflict. And if it's true that a lot of this conflict is occurring at the subnational level, what can these institutions in the Global North learn from other institutions in the Global South? And then particularly, what can we do to facilitate that sort of knowledge transfer?
Wow.
Simple question.
Yeah, I'm not even sure where to begin on that one. From a conflict perspective, part of the challenge is understanding what the root of the conflict is. There are a lot of different, we track a lot of different water conflicts. We track conflicts over water allocation. We track conflicts where the conflict is about something else, but the targets and tools are water systems, which are, again, there's separate histories for all of those. The trend in recent years has been shortage and conflict over water availability and allocation, and frankly, in the Global South, not so much in the Global North. There are lots of examples from the Global North. Part of the problem is we have data from the Global North that's better than the Global South, so there are problems with the data. There are different kinds of conflicts, and of course there are different kinds of management institutions as well. And so I'm not sure the best place to look for lessons and the most appropriate lessons, but I do think that when you have good institutions, the risk of conflict drops. And so you want to look for examples where there are either formal structures in place that can help you manage conflicts or help you manage the things that cause conflict, the allocation of water, disputes when they arise. Then the risk of conflict drops. And sometimes it's transboundary, transnational agreements. Sometimes it's simply water sharing and water rights strategies. So I don't know if I'm really answering your question, but it's a good one.
I think it sounds definitely like a dissertation-worthy question. Just a couple of things to add to that. And I don't know how easy this is to achieve, but data transparency and data sharing can go a long way towards, again, it's sort of the education. Let people see that these are regional problems and they require regional solutions, because when it comes to water, we literally are all in it together. And then the other thing is, enforcing, you can have a treaty or an agreement, but if there's no way to enforce it, right, if there's no teeth, then I don't know how good it is. So it's just, institutions with, or a way to, institutions with teeth, right? That's it.
You can ask it again later.
Yeah.
Simple question. The replenishment of the groundwater is in a specific area depends on the precipitation in that area. This is one. And the second is, is there a rough latitude over which we have weather conditions and
Yes, sure.
dry
Okay.
conditions
Right.
in the north and the south?
So there's the natural replenishment, which comes from rainfall and river flows and infiltration, right, into the aquifers. And then there's the managed recharge, the managed replenishment. And we're doing more and more of that all over the world. And we do plenty of it in Orange County. And some of that water that is being used to recharge aquifers is natural surface water. Say this is the water from upstream in the Santa Ana River. We make it flow through a number of diversions to encourage the recharge of the aquifers. The other thing that we do is we recycle the sewage water and then replenish the aquifers with that as well. So, oh, and then your question on the latitude. Yeah, I mean, there are, you know, the classic, of course I don't know the numbers offhand, but the classic, you know, arid to semi-arid, you know, the arid regions of the world are those mid-latitudes, say 20 to 40, 20 to 50 degrees north and south latitude, where it doesn't rain. Most of our rain falls in the tropics, and it falls at 50 to 60 degrees north latitude. And so in those in between, right, that's where all the deserts are, so call them the subtropics, 10, 20 degrees to 45, 50 degrees north and south latitude. It's mostly, you know, a lot of it's in the northern hemisphere because that's where the land is.
I wanted to ask a question about water exports. As the developing world has a growing taste for meat and dairy, and they send us shipping containers full of finished goods, we're sending them our alfalfa, essentially exporting our water. Also, I know the United States is a top pork exporter, among hundreds and hundreds of other products. What kind of a system is it where we export our water, yet we don't import our water, or if we do, they come in half-liter bottles that we throw happily into the ocean? I mean, is this something that should continue? Is this a bad paradigm? How can this be replaced, and what are we doing to manage it?
So that's a great question. There's a whole field of analysis and study called virtual water, or water footprinting. There are all sorts of interesting analytical tools and papers that have been written about this, which is in a sense what you're talking about. It's the idea that there's water embedded in the goods and services that we transfer around the world. When we're importing meat, we're importing the water, in a sense, that was required to produce that meat. When we export goods and services, in a sense, we're exporting the water that was required to produce those goods and services. We don't move much water around because water, as Jay said, is extremely heavy and it costs a lot to move. You know, we'll move it in aqueducts a few hundreds or maybe 1,000 kilometers or more, but we don't put it in tankers because it's too expensive to move. But it's economically feasible to move goods and services around. I think that's a rational thing. That's the way the economy works. It would be more rational if we priced water properly, so that the true impacts of taking water and moving it from one place to another were adequately reflected in the prices of our goods and services, but we're working on that. We did at the Pacific Institute the first comprehensive water footprint for California, and it's on our website. It was published about a year ago. We looked at the water required to produce the goods and services in California, subtracted out the water required to produce the goods and services that we export, and added back in the water embedded in the goods and services that we import and consume in California. It turns out California is a net importer of water. We grow a lot of food that we export. We grow semiconductors that we export, but we're a net importer. We actually import more water, in a sense, in our net economy. Is that good or is that bad? I don't have an answer to that. That's an economic and a policy question. I did get into an interesting conversation with a friend of mine, a colleague, Robert Glennon, who teaches at the University of Arizona, because he made a comment, it's crazy to export all this alfalfa from California to China, which we do. But the truth is we import more water, Chinese water, in a sense, in the goods and services that we import from China, because we're a bigger consumer of imported goods than we are exporting. Those are tough policy questions, and you said, is it a rational paradigm? Maybe. It's an interesting question to ask, and I think it's a question tied up with the value of water locally, the economy that we've chosen to put in place, and the value of imports and exports, and it would be an interesting conversation to have.
So I just want to add to that the issue of other countries, buying up it. China's buying a lot of land in the United States. Different countries are out, especially the developing countries, or the rapidly growing countries, are buying a lot of land outside of their boundaries to get the water rights, to get the water availability, to get the mineral rights, right? So they're expanding their reach, so to speak. And it's just an interesting story about China and all the land they're buying in the United States.
Actually, let me say one more thing about China in particular. There's a paper in press right now, it's in review, for China's water footprint, in a sense. China has very serious water problems. Northern China's dry, southern China's wet. Northern China is in a serious deficit situation. Their groundwater is being vastly overpumped. There's a conversation going on right now in China about the water footprint of the local provinces. And they've come to realize that they're exporting a huge amount of virtual water, if you will, goods and services that required water to produce, at their own expense, in the sense of deteriorating groundwater, deteriorating water quality, deteriorating surface water availability. And there is a conversation going on in China now that they're doing these studies. Is this a good thing? Our economy is being boosted because we're exporting all these goods and services, but at the cost of local ecosystems and local water quality.
Hi, thank you so much for the presentation. They're terrific. I do some work with Latin American water utilities on issues about upstream conservation, watershed protection. I'm curious about the work that you do, and we were talking before about getting the word out and trying to make sure that this kind of important information that you're sharing percolates out to society. It seems to me that water utilities are an important entity to get it because they manage a lot of water. And I'm curious about your experience. Are they have been conversations with water utilities? Do you find that they're more rational actors because this is their business and they have to get it right in terms of not overdrawing, making sure they have? And I'm particularly interested in public water utilities because they aren't just on X number of your concession contracts. They're actually.
Yeah. What countries do you work in?
Oh, I've been doing some work in with the lead sort of Peru, Ecuador, Colombia, and some more from Mexico as well. So I'm curious about what kind of.
Well, so my guess is that so I'm interested to hear Peter's response as well. But we're going to have two different perspectives because what I do is often, I show people this, and the impact. The response varies a lot, and it varies a lot by individuals. And there is, unfortunately, in academics, there's a bias against working with academics in some of the water management and water utilities because I think that we're arrogant and our stuff is too researchy. So I get a lot of that, especially unfortunately in California. But in other states, it's not federally. I get a lot of interest and a lot of positive response. And then internationally, the only place that I've really worked with directly is in the Middle East and Israel and Jordan and Palestine. And there, the response is quite good. So it's been a little mixed, but maybe I'm a little disappointed by the California response.
We do a lot of work with water utilities. We're an academic organization also, we're a think tank, but we've done a lot of work on water energy connections with water utilities. We do a lot of work on water efficiency and demand management strategies with water utilities. In general, water utilities, their job is to provide a service. Their job is to provide water, to deal with wastewater, and they're customer oriented. They have to figure out reliable supply, they have to figure out proper pricing and financing to make sure that their operations work well. They have to deal with customer service. In general, I find water utilities are very responsive to the problem. They're really aware of concerns about supply and demand. They're really concerned about financial sustainability. There are public versus private. There's a whole separate debate about public versus private. I asked what countries, in part because there are a number of South American countries that have moved very strongly toward a private water utility system, Chile in particular, but not alone. The US is dominated primarily by a public water system. 85% of our population gets water from public water agencies. The Institute, the Pacific Institute, has done a lot of work on the issue of privatization and advantages and disadvantages of different models, but all water utilities, public or private, are monopolies. And so there's government oversight, or there ought to be government oversight and regulatory oversight to make sure that operations are not monopolistic, if you will, and sustainable. One area where utilities have not done a good job because they don't really know how to deal with it is the issue of climate change. Either they don't understand it, or they don't believe it's happening, or they don't know how to deal with it. Their projections about water are based on past climate. Their hydrologists are trained to assume that the future is going to look like the past, and that's not the case. So we haven't had much good experience with getting water utilities to think about long-term perspectives. Even though they build infrastructure that lasts 50 years, they're not that good at that issue, and I think that's a challenge. So